Hello everyone, and welcome. Today, we're diving into a critical topic that underpins much of the technology we rely on and the future we're building: rare earth materials. While often unseen and unheard of by most, these elements are the secret ingredients powering our smartphones, electric vehicles, renewable energy, and so much more. Let's explore the fact. Hello everyone, and welcome. Today, we're diving into a critical topic that underpins much of the technology we rely on and the future we're building: fascinating, and sometimes concerning, world of rare earths. So, what exactly are we talking about when we say rare earth? Fascinating, and sometimes concerning, world of rare earths. So, what exactly are we talking about when materials? Despite the name, they're not actually that rare in the Earth's crust. Instead, it's their economic extraction that presents the real challenge. We're referring to a group of 17 elements, officially called rare earth elements, or REES for short. These are typically divided into two categories: light rare earths, ranging from lanthanum to gadolinium, and heavy rare earths, from terbium to lutetium, along with yttrium. What makes them so special? It's their unique properties. REES boast exceptional magnetic, luminescent, electrochemical, and catalytic characteristics. Think of them as nature's multi-tools at the atomic level. These properties are what make them indispensable in modern technology. It's a bit of a misnomer to call them rare in terms of abundance, but their geological distribution and complex extraction processes certainly make them a strategically valuable resource. Now, let's bring this into focus and see just how crucial REES are in the technologies shaping our lives. Look around you, at your smartphone, laptop, or the screen you're viewing this presentation on. Rare earths are essential components in the displays and internal electronics. But their importance goes far beyond consumer electronics. The green energy revolution is fundamentally reliant on REES. Wind turbines, electric vehicles, and even solar panels utilize these materials for high-performance magnets and efficient energy conversion. Our defense and aerospace industries depend on them for radar systems, satellites, and the guidance systems of advanced missiles. Even in medicine, from MRI machines to laser surgery, rare earth elements are playing a vital role in diagnostics and treatment. And as we look to the future, into emerging technologies like quantum computing, neuromorphic chips mimicking the human brain, and advanced AI hardware, the demand for specialized rare earths is only going to intensify. They are truly the unsung heroes of the modern technological age. Let's get a bit more specific and highlight some key rare earth elements and their applications. Neodymium, or Nd, is a powerhouse when it comes to magnets. It's the key ingredient in the powerful magnets used in electric vehicle motors, wind turbines, and even the cooling systems in data centers that power the internet. Dysprosium, Di, acts like a performance enhancer for these magnets, especially in high-temperature environments, making them more reliable and efficient. Lanthanum, La, is incredibly versatile. You'll find it in camera lenses, enhancing clarity, in advanced EV batteries boosting performance, and even in hydrogen storage technologies, which are vital for a clean energy future. Yttrium, Y, while technically not a lanthanide but often grouped with REES, is critical in superconductors, bright LED displays, and cutting-edge quantum dot technologies. Cerium, Ce, is a workhorse in catalytic converters, reducing harmful emissions from vehicles, as well as in glass polishing and water treatment processes. And finally, praseodymium, Pr, is used alongside neodymium to create high-strength magnets, in lasers for various applications, and in specialized glasses with unique optical properties. Each of these elements, among others, plays a unique and often irreplaceable role. Now, for the less comfortable part of the story, the global supply chain and our dependency. Currently, the vast majority of rare earth material production is concentrated in a few countries. China dominates the landscape, controlling an estimated 60 to 70% of global supply. While the USA, with the Mountain Pass mine reopening, and Australia, with the Mount Weld mine, are significant players, and emerging producers like Myanmar, Vietnam, and Brazil are entering the scene, China's processing capacity is even more dominant, controlling around 85% of the global infrastructure needed to refine these raw materials. This concentration creates significant supply chain risks. Trade restrictions, geopolitical tensions, and the potential for resource scarcity become major concerns when a single nation holds such a dominant position. Furthermore, the environmental impact of rare earth mining is substantial, with consequences ranging from landscape disruption and water pollution to concerns about radioactive waste. This dependency and its associated risks are not just economic considerations, they are increasingly becoming matters of national security. These supply chain vulnerabilities are directly impacting the market right now. We've seen dramatic price volatility, with some rare earth elements experiencing price increases of 200 to 400% since 2020. In response, nations are engaging in strategic stockpiling, building up reserves of these critical materials to buffer against supply disruptions. We're also seeing increasing export controls, with major producers implementing restrictions on rare earth exports to prioritize domestic needs or exert geopolitical influence. To mitigate risks, some tech companies are pursuing vertical integration, investing directly in mining and processing to secure their own supply chains. And looking to the future, there's exploration of emerging supply sources, including the very ambitious concept of deep-sea mining and asteroid mining research, though these are still in early stages. Looking ahead, the demand picture is only pointing upwards. The projected surge in demand for electric vehicles, AI, hardware, and renewable energy technologies will place immense pressure on rare earth supply. For example, EV production alone is expected to require 40% more rare earths by 2030. Wind turbine installations are projected to use 250% more by 2035. And the growth of quantum computing and specialized AI chips will drive demand for even more specialized rare earths. This booming demand is colliding with significant supply constraints, including limited refining facilities and the geopolitical dependencies we discussed. We face an energy transition paradox. The very green technologies we need to combat climate change are reliant on materials with environmentally problematic extraction processes. Furthermore, geopolitical competition over these critical minerals is intensifying, with rare earths becoming a key battleground in international trade and security. So, what can be done to mitigate these risks and reduce our dependency? Several strategies are emerging. Diversification is key, developing new mining projects outside of China. Initiatives like the European Rare Earths Alliance, the North American Critical Minerals Strategy, and the Australian Critical Minerals Accelerator all aimed at fostering domestic and regional production. Recycling offers another crucial avenue. Recovering rare earth metals from e-waste and end-of-life batteries, often referred to as urban mining, could yield a significant percentage of our critical re-needs, potentially up to 35% for some elements. New chemical processes are being developed to make this recycling more efficient. And crucially, research and innovation are vital. Material substitution programs aim to reduce the re-content in technologies, with potential reductions of 20 to 30%. Nanotechnology is exploring ways to use REES more efficiently, and scientists are actively seeking synthetic alternatives to replace REES in specific applications. These strategies offer a path towards a more secure and sustainable future. On a hopeful note, let's highlight some exciting technological breakthroughs that are emerging. Rare earth-free magnets, using iron nitride alternatives, are showing significant promise and could potentially reduce our reliance on neodymium and dysprosium. Hybrid motors are being designed to reduce or even eliminate rare earths in certain electric vehicle applications. Enhanced recycling technologies are advancing rapidly, with new processes capable of recovering up to 95% of rare earths from waste streams. Circular design principles are becoming more important, with products being engineered from the outset for easier rare earth recovery and reuse at the end of their life. And even biological extraction methods, using bacteria-based mining processes, are being explored to reduce the environmental impact of rare earth mining. These technological advancements need to be supported by robust policy and industry responses. We're seeing new critical materials legislation being enacted in various countries to promote domestic production and secure supply chains. International partnerships are crucial, with technology sharing agreements aimed at improving processing capabilities across different nations. Supply chain transparency is becoming increasingly important, with blockchain technology being explored to track responsible sourcing and ensure ethical practices. Industry consortiums are forming to facilitate collaborative R&D on alternatives and recycling solutions. And fostering academic industry partnerships is essential to accelerate the commercialization of these breakthrough technologies and bring them to market faster. A coordinated and collaborative effort is needed across sectors and nations. In conclusion, rare earth elements remain absolutely critical for our future technological advancements. However, our current reliance on a vulnerable supply chain presents significant challenges. Moving forward, we must prioritize sustainable sourcing, invest in robust recycling infrastructure, and aggressively pursue diversification strategies. Collaboration between industries, governments, and research institutions is essential to develop long-term, resilient solutions. Ultimately, we need to strike a balance, harnessing the power of technology for progress while ensuring environmental stewardship and responsible resource management. Strategic planning and decisive action are required to navigate this transition and build more secure and sustainable rare earth supply chains for the technologies of tomorrow. Thank you for your time. Now,